Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual ferment of late 19th century Paris provided a fertile crucible for the emergence of a mind that would profoundly reshape the landscape of mathematics and, by extension, our understanding of the universe. Henri Poincaré, a figure of remarkable breadth and unparalleled depth, stands as a titan whose work continues to resonate across disciplines. His early career was forged in an era grappling with the increasing complexity of mathematical thought, an era where the very nature of geometric form and the qualitative behavior of systems were subjects of intense investigation. The prevailing mathematical currents of the time presented significant challenges. Mathematicians were exploring spaces of ever-increasing dimensions and intricate structures, yet the tools for distinguishing these spaces from one another remained relatively rudimentary. While algebraic methods had achieved great success in analyzing specific geometric properties, a more general framework for understanding the intrinsic, invariant characteristics of shapes, properties that persisted even under continuous deformation, was urgently needed. This quest for invariant descriptors, for a way to classify and differentiate topological spaces, was a central problem that occupied many of the era's most brilliant minds. Poincaré's response to these challenges was nothing short of revolutionary. He introduced a suite of algebraic invariants designed to capture the essential topological nature of spaces. Among his most significant early contributions were the Betti numbers, named in honor of the Italian mathematician Enrico Betti. These numbers quantify the number of independent holes of various dimensions within a topological space. For instance, a simple loop in three-dimensional space contributes 1 to the first Betti number, reflecting a one-dimensional hole. A hollow sphere contributes 1 to the second Betti number, signifying a two-dimensional void. These numbers provided a concrete, calculable means of distinguishing between spaces that might otherwise appear topologically similar. Complementing the Betti numbers, Poincaré developed the concept of the fundamental group, often referred to as the first homotopy group. This algebraic structure, derived from the paths within a space, and how they can be continuously deformed into one another, offered a more powerful invariant. The fundamental group captures information about one-dimensional connectivity in a way the Betti numbers alone could not. Consider a torus, the surface of a donut. It possesses two fundamentally different types of loops that cannot be continuously deformed into each other, one that encircles the hole through the center, and another that goes around the hole on the surface. The fundamental group of the torus elegantly encodes this distinction, revealing a richness of topological structure that simple hole counting might miss. These innovations, presented in his seminal 1995 work, Analysis marked the birth of modern algebraic topology. Poincaré established a program for studying topology through algebraic means, a paradigm that would dominate the field for decades. He recognized that the interplay between geometry and algebra was key to unlocking deeper truths about the nature of space. His work provided the essential language and conceptual tools for mathematicians to rigorously classify and understand the connectivity and structure of complex manifolds and other geometric objects. The impact was immediate and far-reaching, providing a systematic approach to problems that had previously been tackled through more ad hoc geometric intuition. The significance of these foundational concepts extends far beyond their immediate utility in classifying spaces. Poincaré's Betti numbers and fundamental group provided a robust algebraic framework that allowed mathematicians to translate geometric questions into algebraic ones, a powerful heuristic that has driven progress across numerous mathematical fields. The very idea of using algebraic invariants to study geometric properties became a cornerstone of mathematical research. His work demonstrated that seemingly abstract algebraic structures could serve as precise probes for the intrinsic nature of geometric forms, revealing their fundamental character in a way that visual inspection alone could not. Yet, even as he laid these powerful foundations, Poincaré posed questions that would challenge generations of mathematicians. His work on the fundamental group in particular hinted at deeper connections between the algebraic invariants and the underlying geometric structure of spaces. This line of inquiry led him to formulate conjectures about the relationship between the homology groups closely related to Betti numbers and the fundamental group of a manifold, particularly concerning spheres. The famous Poincaré conjecture concerning simply connected, closed three manifolds remained a tantalizing open problem for over a century, a testament to the profound depth and subtlety of the questions he raised. His explorations in analysis were not merely solutions to existing problems, but the genesis of entirely new avenues of mathematical inquiry, pushing the boundaries of what was understood about the very fabric of space. His insights provided the essential scaffolding upon which much of contemporary topology and geometry has been built. Poincaré's intellectual reach extended profoundly into the realm of physics, where he grappled with fundamental questions that animated the scientific discourse of his era. The stability of the solar system, a problem that had occupied astronomers and mathematicians for centuries, presented a formidable challenge within the framework of Newtonian mechanics. The intricate gravitational interactions among the sun and its planets, Particularly, the moon's influence on Earth led to complex differential equations whose solutions resisted precise analytical determination. The famous three-body problem, a specific instance of these celestial mechanics, demonstrated the inherent difficulty in predicting the long-term behavior of even a few interacting bodies. Poincaré approached these dynamical systems with a novel mathematical arsenal. He pioneered the development of qualitative analysis for differential equations, a methodology that focused on the overall behavior and structure of solutions rather than their explicit computation. This involved visualizing trajectories in phase space, identifying stable and unstable equilibrium points, and characterizing periodic orbits. His seminal work, New Methods of Celestial Mechanics, published in 3 volumes between 1888 and 1899, revolutionized the field. Within its pages, Poincaré introduced concepts that would later form the bedrock of chaos theory. He observed that in many such systems, small changes in initial conditions could lead to dramatically different outcomes over time, a phenomenon he termed sensitive dependence on initial conditions. This insight challenged the deterministic certainty that had long been a cornerstone of classical physics, suggesting a universe where predictability had inherent limits. The mathematical tools Poincaré forged for analyzing these complex systems, such as the study of periodic orbits and their stability, and the concept of invariant manifolds, provided a new language for describing the intricate dance of celestial bodies. He demonstrated that the solar system, while appearing stable over human timescales, might exhibit chaotic behavior over vast cosmological epochs, a profound revaluation of cosmic order. His work provided the essential framework for understanding the long-term evolution of planetary orbits, moving beyond simple approximations to a more nuanced appreciation of the inherent complexity. Parallel to his work in celestial mechanics, Poincaré made seminal contributions to the understanding of electromagnetism, particularly in relation to Maxwell's equations. The prevailing view of the electromagnetic field was that it propagated through a luminiferous ether, a hypothetical medium filling all of space. However, experimental results, such as the Michelson-Morley experiment, failed to detect this ether, creating a significant conceptual void. Poincaré engaged deeply with these issues, seeking to reconcile electrodynamics with the principles of mechanics. He articulated the principle of relativity, suggesting that the laws of physics should be the same for all uniformly moving observers. This was a critical step towards special relativity. Poincaré explored the implications of Lorentz transformations, which had been developed by Hendrik Lorentz and Joseph Larmor to explain the null results of ether drift experiments. Poincaré recognized that these transformations preserved the form of Maxwell's equations and had a deeper geometric meaning. He considered the possibility that the speed of light in a vacuum might be an invariant, a universal speed limit. In a lecture delivered in 19 and a more formal presentation in 1904, Poincaré discussed the structure of spacetime and the transformations that relate different inertial frames. He proposed that time itself might be relative, contracting for moving bodies, and that length measurements would also be affected. His work foreshadowed the concept of spacetime as a unified entity, where space and time are intertwined. He even considered the implications of these transformations for the addition of velocities, anticipating the relativistic velocity addition formula. While he did not formulate the complete theory of special relativity with its geometric interpretation of gravity, his insights into the relativity principle, the invariance of the speed of light, and the transformations connecting inertial frames were foundational. He provided the mathematical scaffolding and conceptual clarity that paved the way for Einstein's groundbreaking work. Poincaré's exploration of electromagnetic waves and their behavior also led him to consider the nature of radiation and energy. His understanding of Maxwell's equations allowed him to analyze the propagation of electromagnetic disturbances and their interaction with matter. He contributed to the understanding of phenomena such as the Doppler effect for light and the behavior of electromagnetic fields in various media. His rigorous mathematical treatment of these physical phenomena provided a deeper understanding of the underlying principles governing light and electricity. The problems Poincaré addressed in physics were not merely academic curiosities. They were central to understanding the fundamental forces and constituents of the universe. The apparent paradoxes in electromagnetism and the challenges in celestial mechanics demanded new theoretical frameworks. Poincaré's approach was characterized by profound respect for mathematical rigor coupled with a keen physical intuition. He sought to build a consistent and coherent picture of the physical world using mathematics as his primary tool. His development of qualitative methods for differential equations offered a powerful new lens through which to view the dynamics of physical systems. This approach allowed for the analysis of systems that were analytically intractable, revealing hidden patterns and behaviors. The concepts he introduced, such as limit cycles and strange attractors, though the latter term came much later, provided the conceptual tools to describe phenomena that were previously considered random or inexplicable. Poincaré's work on relativity, though predating Einstein's definitive formulation, demonstrated a remarkable prescience about the fundamental structure of space and time. He recognized the limitations of the Galilean transformations and explored the mathematical consequences of a constant speed of light. His willingness to question established notions and to follow the logical implications of mathematical principles wherever they led was characteristic of his scientific genius. He saw the interconnectedness of mathematical structures and physical reality, understanding that advances in one domain often eliminated the other. His legacy in physics lies in the profound mathematical frameworks he created, which continue to inform our understanding of the universe. The intellectual landscape at the turn of the 20th century was a fertile ground for profound philosophical inquiry into the very nature of scientific knowledge. As established paradigms in physics and mathematics faced new challenges and revelations, thinkers grappled with fundamental questions about how we know what we know, the relationship between abstract mathematical constructs and the tangible world, and the criteria that elevate an idea to the status of scientific. It was within this dynamic intellectual milieu that Henri Poincaré's unique philosophical perspective emerged, offering a unifying vision that bridged the rigorous demands of mathematical proof with the empirical realities of physical observation. Poincaré's most significant philosophical contribution and a cornerstone of his interdisciplinary synthesis was a sophisticated articulation of conventionalism. This viewpoint offered a compelling response to the challenges posed by the evolving foundations of geometry and physics. He argued that certain fundamental principles, particularly those underpinning our understanding of space and time, functioned less as absolute empirical discoveries and more as useful, albeit arbitrary, conventions. This was a radical departure from the prevailing view that scientific laws were direct transcriptions of an objective external reality. Consider, for instance, the geometry of space. For centuries, Euclidean geometry, with its seemingly self-evident axioms, was considered the only possible description of physical space. However, the development of non-Euclidean geometries by mathematicians like Gauss, Lobachevsky, and Riemann demonstrated that alternative, internally consistent geometric systems were mathematically viable. This raised a crucial question: which geometry accurately described the physical universe? Poincaré's conventionalism provided a framework for addressing this. He proposed that the choice between Euclidean and non-Euclidean geometries for describing physical space was a matter of convenience and utility, rather than one of absolute truth. The geometry that yielded the simplest and most elegant mathematical formulations for physical laws would naturally be preferred. This perspective allowed scientists to embrace the mathematical richness of non-Euclidean geometries without abandoning the empirical grounding of their work. The choice of geometry became a methodological decision, a tool to simplify the description of physical phenomena rather than a direct apprehension of reality's intrinsic form. This philosophical stance was particularly prescient in light of emerging physical theories. Poincaré recognized that the structure of space and time, as understood through Newtonian physics, was not necessarily immutable. His own work on the electrodynamics of electrons and his exploration of the consequences of the constant speed of light foreshadowed the radical reevaluation of space and time that Albert Einstein would later formalize in his theory of special relativity. Poincaré saw that the mathematical framework required to describe phenomena at high velocities and near the speed of light necessitated a departure from the absolute concepts of space and time inherited from Newton. He understood that the mathematical tools we employ to model the universe are not necessarily dictated by the universe itself, but are often chosen for their explanatory power and predictive accuracy. His exploration of the principle of relativity, a concept he articulated with remarkable clarity before Einstein's definitive work, exemplifies this. Poincaré understood that the laws of physics should possess a certain invariance, meaning they should hold true regardless of the observer's state of motion. This invariance, he argued, was a fundamental symmetry that physics should strive to preserve. The mathematical transformations that preserved these laws, such as the Lorentz transformations, were not necessarily revelations of an absolute spatial or temporal structure, but rather the necessary mathematical scaffolding to maintain the internal consistency and symmetry of physical descriptions. He saw these transformations as conventions that enabled a coherent description of phenomena across different inertial frames of reference. Poincaré's philosophy also extended to the nature of scientific laws themselves. He viewed scientific laws not as immutable truths, but as powerful generalizations derived from observations, refined through mathematical modeling, and subject to revision. The success of a scientific theory, in his view, lay in its ability to provide a coherent and predictive account of the world, to unify diverse phenomena under a common framework, and to offer a sense of order and intelligibility. This emphasis on the explanatory power and predictive success of theories, rather than their absolute correspondence to an unknowable reality, resonated deeply with the pragmatic spirit of scientific inquiry. He understood that the process of scientific discovery involved a delicate interplay between intuition, rigorous logical deduction, and empirical verification. Mathematicians and physicists often develop an intuitive grasp of underlying structures, which is then formalized through mathematical language. This formalization, however, is not a passive reflection of reality but an active construction. The choice of mathematical concepts, axioms, and methods involves a degree of freedom, a selection process guided by principles of simplicity, elegance, and explanatory efficacy. Poincaré's philosophy provided a philosophical justification for this creative aspect of science, acknowledging that the human mind plays an active role in shaping our understanding of the universe. This interdisciplinary synthesis was profoundly impactful. By grounding his philosophical reflections in his deep engagement with mathematical and physical problems, Poincaré offered a nuanced understanding of scientific progress. He acknowledged the limitations of human knowledge and the provisional nature of scientific theories, while simultaneously celebrating the power of human reason and mathematical ingenuity to unravel the complexities of the cosmos. His work encouraged a more flexible and dynamic view of science, one that was open to revision and innovation, and that recognized the crucial role of human interpretation and conceptualization in building our scientific worldview. He demonstrated that the abstract beauty of mathematics and the concrete realities of the physical world were not separate domains but intimately intertwined, each informing and enriching the other. This seamless integration of mathematical insight, physical intuition, and philosophical reasoning characterized Poincaré's unique genius and continues to offer a profound model for understanding the nature of scientific endeavor. His philosophical contributions provided a vital intellectual bridge, allowing for the assimilation of revolutionary new ideas in physics without succumbing to epistemological uncertainty. Henri Poincaré's intellectual journey, a testament to the profound interplay between abstract thought and empirical observation, left an indelible mark on the landscape of modern science and philosophy. His investigations into the dynamics of celestial bodies, initially framed within the classical mechanics of Newton, gradually revealed the intricate, often unpredictable, nature of physical systems. This exploration, particularly his work on the three-body problem, foreshadowed a revolution in understanding complex systems, a realm where precise prediction often eludes even the most sophisticated mathematical tools. The sensitivity of solutions to initial conditions, a concept that would later find its definitive expression in chaos theory, was a concept Poincaré grappled with, recognizing that the elegant determinism of Newtonian physics might possess a subtler, more nuanced reality when applied to systems with multiple interacting components. His contributions to topology, a field he helped to forge, offered a new language for describing shape and form divorced from specific measurements or coordinates. This abstract, qualitative approach to geometry provided powerful new methods for analyzing structures and transformations, proving invaluable in fields as diverse as differential equations and theoretical physics. The Poincaré conjecture, a problem that would occupy mathematicians for a century, stands as a testament to his visionary thinking in this area, probing the fundamental nature of three-dimensional spaces. His development of the concept of the fundamental group, a way to characterize the holes in a topological space, provided a crucial tool for distinguishing between different shapes, a foundational element for later developments in algebraic topology. Poincaré's engagement with the philosophy of science offered a vital framework for interpreting the seismic shifts occurring in physics at the turn of the 20th century. He championed a pragmatic view of scientific theories, seeing them as useful conceptual tools for organizing experience rather than absolute reflections of an underlying reality. This perspective allowed him to embrace the revolutionary ideas of relativity and quantum mechanics, not as demolitions of previous scientific understanding, but as extensions and refinements, offering new lenses through which to view the universe. His emphasis on the role of convention and the human mind in constructing scientific knowledge provided a crucial intellectual bridge, allowing for the assimilation of these paradigm-shifting concepts without succumbing to epistemological uncertainty. He demonstrated that the abstract beauty of mathematics and the concrete realities of the physical world were not separate domains but intimately intertwined, each informing and enriching the other. This seamless integration of mathematical insight, physical intuition, and philosophical reasoning characterized Poincaré's unique genius and continues to offer a profound model for understanding the nature of scientific endeavor. His legacy is one that encourages a more flexible and dynamic view of science, one that is open to revision and innovation, and that recognizes the crucial role of human interpretation and conceptualization in building our scientific worldview. He celebrated the power of human reason and mathematical ingenuity to unravel the complexities of the cosmos, while simultaneously fostering an appreciation for the inherent limitations and evolving nature of scientific knowledge. Poincaré's enduring influence lies in his ability to synthesize diverse fields, to ask fundamental questions about the nature of reality and our knowledge of it, and to develop the mathematical and philosophical tools to pursue those questions with rigor and imagination. His work remains a beacon for anyone seeking to understand the intricate relationship between the formal structures of mathematics and the unfolding mysteries of the physical universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.